3 years ago, I moved to Montpellier, south of France. I joined Teads and had the privilege to work on a project that was called BigQuery POC at the time. Today, I am thrilled to be back in Paris to showcase how this project has grown from a proof of concept to a data pipeline that is able to give meaning to 100 billion events per day. But first, a few words about Teads. Anyone heard about Teads? Not a lot. Although I'm pretty sure you regularly see ads served by Teads on these news publishers. We're an ad tech company. We have united the best publishers in the world into what we call the global media platform. With Teads, advertisers can reach 1.5 billion people monthly. It's growing so fast, it's even hard to keep slides up to date. We serve ads at scale within a premium context. Now, why do we even need data? This is the kind of user interface that we want to show for our clients, for publishers to monitor their inventory and revenue, and for advertisers to manage their campaigns. It's full of dashboards where you can show plenty of metrics and explore multiple dimensions. We want a fast and interactive user experience. And to do that, we need to collect, store, and process hundreds of billions of events per day. Let's take a look at the source of these events. And to do that, we need an ad break. So what happened here? To know what's going on, this ad experience emitted 5 events. The first one is ad slot available. That's when there's room for an ad inside the web page. Then we have ad available. This is the result of a complex auction system that is running behind the scenes to select the right ad for the right time at the right price. Impression is when the ad is actually displayed. And then user click and video complete are useful metrics for advertisers. 100 billion events a day, that's more than 1 million events per second that we have to store, collect, and process to give meaning to these events. Another important metric is 10. We're only a team of 10 people to build, operate, and maintain a data pipeline that give meanings to these events. So that's why we are more than happy to rely on managed infrastructure such as BigQuery and Redshift to help with the complexity that comes with that scale. So we have an ad experience emitting events on one side, and we have applications with data visualization on the other hand. What goes in the middle? If we want to oversimplify, we can simply say we store this in a database. At least that's what I say to my parents at Christmas when they ask what I do. But we all know in this room that it's a little bit more complex than that. The first thing we want to do when we receive those events is to store them ASAP on disk so that whatever happens, we can find them back. Kafka is the perfect tool for that. The tracker here is a simple HTTP server that receives the message and stores it in Kafka. Then out of Kafka, we can take the time to asynchronously store these events into a database. And the good thing with Kafka is you can read the same events to do other stuff, say machine learning. At Teads, we use BigQuery as a data warehouse to store these events. Then we extract data marts from this data warehouse that we store into Redshift. As you may guess, it's still a bit more complex than that. Tracker, data warehouse, data marts. I'll open each of these boxes so you can see what's inside. Let's start with the tracker. The job of the tracker is simply to read individual events and to store them into Kafka. Sounds simple enough. Now, because the messages in Kafka are read by multiple clients to do different stuff, the tracker is the last place where we can mutualize a common business logic before these events are used by all. Here are examples of business logic. We can get geolocation from IP. We can remove the IP from events. We can get the device information from user agents. And we can hydrate the event with dimension tables. Now, with a growing amount of events to handle and more business logic to apply, we got into a problem. The primary goal of the tracker to write events ASAP into Kafka was being jeopardized. Should anything go wrong inside the tracker or the infrastructure it depends on, we are at least at risk of losing events. And losing events basically means the ad never existed, thus it is a net loss for us. The solution we found is to split the tracker into two different services. The first one, the tracker collector, is a very simple HTTP server based on Netty. Its only job is to collect the events and store them ASAP into Kafka. Because this service is critical, we try to keep the code very straightforward, and it has no dependency on external services, such as a database. Now, the second component, the tracker hydrator, is a bit more complex. It handles all the business logic and the dependencies to external databases. Because it can work asynchronously, it can start, resume tasks, we are much more confident when we deploy it that if something's wrong and we have downtime, we know the events are still in the first Kafka topic. So it gives us more confidence to deploy more and more business logic into this asynchronous tracker. We chose Flink to be able to do stateful computations while streaming the data. With the tracker, we safely store the events into Kafka and then asynchronously hydrate them so they contain meaningful business logic. One of the main consumers of this Kafka topic is our data warehouse based on BigQuery. Let's open that box. We chose data flow to move data from Kafka to BigQuery. But unlike common ETL approach, we have chosen an ELT approach. Let's have a look at what it means. ELT means we first load everything into BigQuery, and the transformation is entirely handled by BigQuery. So all the events are batch loaded into temporary tables. So each table contains about 30 minutes of data. Then inside BigQuery, we have a lot of jobs that can process the data. I'll give you two examples. The first one is a very straightforward job that takes the events and appends them into a single federated table. This table is really important for us to be able to explore the data and for debug purposes too. Another job more complex is the rollup job. It has two missions. The first one is to aggregate the data into separate tables, one per hour, so we can know where to find events. And the second job is to aggregate these events so it's much faster to query. Let's have a look at this job. With these 5 events as examples, we have for each event a timestamp, an ad ID, website ID, and the name of the event. And we want, in this example, to group by 3 dimensions: the hour, that is derivated from the timestamp, and the ad ID and website ID. And we want to compute 3 metrics, the number of impressions, of starts, and clicks. In this example, we have reached a 2.5x compression ratio, whereas in real life, the compression is more about 50x. Now, before BigQuery, to do these aggregations at scale, we used Spark jobs written in Scala with all the complexity that comes with it. With BigQuery, it has been simplified into a single SQL query. This is the same query as the example. As you can see, you only have to group by your dimensions and compute your matrix. In real life, we have 60 dimensions and 150 metrics. So you can imagine the query is much longer, but I can assure you it's as simple as that, only bigger. Now, despite running this query on a batch of 100 million rows, and that's about 25 gigabytes of data, it takes only 1 minute and 40 seconds to compute. And the good thing about it is it didn't even use all the capacity of BigQuery, because if it did, it would have taken only 8 seconds. So it means you have plenty of room to run other jobs in parallel. What did we learn with BigQuery? BigQuery combines the simplicity and performance. It has very low maintenance for what it does. And most importantly, its simplicity made data accessible. Thanks to SQL, a UI with single sign-on, it is a game changer for data exploration when you compare it to what we had before Jupyter Notebooks in Scala. So, and also at this scale, BigQuery flat rate is mandatory for us. It has predictable costs, and because the price is fixed, it also drives usage. We at first had only one team using it. Now about half of the teams at Teads use BigQuery for production jobs, and all the teams use it for data exploration. Now, however, it requires workload management. With BigQuery, by default, if you run all your queries into a single GCP project, you are not able to have different SLAs or priority by query or by service. To split workloads, you have to separate them into several projects. When you do that, you give a hint to the BigQuery scheduler to give a fair share of slots, the computational capacity of BigQuery, to each of the projects. Now, if you want to go further and say, OK, this project is more important than others, I want to have more priority, it's possible with advanced stuff they call hierarchical reservation, where you say this project has more priority or can access more slots than others. So that's one of the hard stuff when you use BigQuery with flat rate, is managing your workloads so that no query can starve the others. All right, now we have aggregated all the data in our data warehouse. Can we just plug the data visualization directly on BigQuery? Well, we don't for several reasons. The first reason is that our data in BigQuery is a bit raw. We need a dedicated service that knows how to query BigQuery and hydrate the result with more business logic. That includes joining with our MySQL database and exchange rate services, for example. With this service, we are able to pull on-demand spreadsheet reports, which is good. And an alternative output for this kind of reports is what we call data marts. So what's a data mart? A data mart is simply a subset of the data warehouse dedicated to a business need. And to give you an idea, these order of magnitude are the main reason why we do rollups and data marts. For every single line inside the data marts, there is 300 lines into the rollup table, and there's 16,000 events in the raw table log. Now, in our case, a data mart is just a table that we store on Redshift. It would have been simpler for us to use BigQuery 2 to store these data marts, but we chose Redshift. I'll tell you why. Before Redshift, and before we even had web apps with interactive visualization, we only had Chart.io, which is data visualization tool that we use internally. And we had IEE, which stands for InfoBright Enterprise Edition. It's a proprietary fork of MySQL, column-oriented. And we used this technology to write data marts that were used by Chart.io. IEE was already reaching its limits, and we had incentive to move away from it. The most naive solution would have been to replace it with BigQuery. We faced two limitations, though. First, BigQuery has a minimum query latency of about 5 seconds, even for small queries on small data sets. For Chart.io, it could work, even though it's not ideal, but Chart.io has a built-in cache, so most of the time you would not even notice. But for web apps with interactive user experience, it was a no-go. We wanted to have sub-second latency. And the second issue with BigQuery is the limit of concurrent queries you can run. By default, you can only run 50 concurrent queries, and we knew it would not scale. Another option would have been to keep IEE for Chart.io, and then use a key-value store as a backend for our web apps. It would have worked, but it would have been very expensive to put in place and to make evolve. The last option we choose is to put Redshift everywhere. It was the perfect match for our Chart.io need. It was kind of a 1-1 replacement with IEE. But it was a counterintuitive choice for data visualization tools, because for two reasons. One, we didn't know, although we know that Redshift is powerful enough for analytical purposes, we didn't know if with small enough query and optimized enough query, we could reach sub-second latency. After some tests and in production, it proved that it worked. The second issue is the same as BigQuery, is the concurrency limit. Redshift by default has 15 concurrent queries. You can scale it up to 50 or 100. I don't remember. But we chose to go with Redshift anyway and to take that risk because we know it was an acceptable risk for two reasons. First, each app is a back office app with a small number of concurrent users. And second, because of the cheap entry price of Redshift, we knew we could scale not the nodes of each Redshift cluster, but also the number of Redshift clusters. So we dedicated one Redshift cluster for each web application, and so we could scale the number of concurrent queries. We were immediately seduced by this solution because it had two great advantages. First, the data modelization would be the same as we already used for data marts in IEE. And second, Redshift would offer much more flexibility for the developers of the apps, as SQL simplifies a lot data visualization, at least compared to a key-value store. The good thing with Redshift, it's cheap entry price. We have been able to easily scale it. Now, by using Redshift, we discovered that despite having a managed infrastructure, it still requires a lot of tuning to work properly. You have to turn a few knobs like sizing, column encoding, sort keys, vacuum, analyze, queues and priorities, instance reservation, and so on and so forth. So it's a much less managed experience than BigQuery, but again, it's two different use cases. Also, user access right is an hassle. It's based on Postgres 8, if you know it. It actually discourages us to give direct access to our data analysts. So we prefer BigQuery for that with the single sign-on and the UI. Now, a few words about how we orchestrate and schedule all that. We use a very simple combination of Jenkins plus an internal tool that we call job history. We have tried alternatives such as Airflow, but the approach was too different from what we were used to, so we decided to invest a bit more into industrializing our Jenkins and this internal tool. So job history is a passive tool that only knows what the history of a given job, what has been processed, what has been not processed, what is need to be reprocessed, and so on and so forth. And it also knows the dependencies between projects. So if a dependency is not ready, it knows that this given project should not be scheduled yet. So Jenkins' role here is simply pull job history and ask it often, what's the next date to process for this job? And when there's a date, it can schedule a job on the analytics service. It's as simple as that, and it works great. You just have to apply a few good practices to make it reliable. For instance, to make all your jobs idempotent, so you can rerun them, for example. And also to rely as much as possible on real data than on metadata. For example, if you want to know if a table is there, just ask the database rather than ask for some service that would have some knowledge about it. All right, we have arrived. I hope you now have a better understanding of the journey of an analytics event at Teads, from the ad experience to the data visualization, going through tracker, data warehouse, and data marts. One question remains, though. Is this data pipeline sufficient to handle 100 billion events a day? The answer is not without challenges. One recent example is our VPN between AWS and GCP that has been saturated to about 1 gigabytes per second. While we love to work on having always bigger pipelines, the smartest solutions is often elsewhere. Before investing into more infrastructure, we always ask ourselves, if we have big data, could we have fit data instead? Do you really need to analyze all the events, or can you make do with a statistical approximation with sampling? Are all of these events useful? Can you just remove some of the old events you don't need anymore? Do you really need all the fields from all the messages, or could you clean up and reduce the size of the messages? For instance, at Teads, we sample a lot, and only 10% of the total events are actually analyzed. So the first answer to how we give meaning to 100 billion events a day is we trash 90 billion of them. If you want to know more about our data pipeline or our technical challenging at Teads, we have written phenomenal articles on our engineering blogs. And honestly, they're great. And I'm not only saying that because I wrote 2 of them. They cover more topics such as how we use BigQuery flat price, intercloud data transfer problems, Redshift optimizations, AWS cost management, and more. And if, like me, you like technical challenges and quality of life, we are hiring in Montpellier.